Alright, so this is going to be the last, hopefully the last part of section 1.4. It's the word problems that involve instantaneous rates of change. And the important thing that I want you to focus on in the word problems is what the number that when you calculate the instantaneous rate of change, it's going to be a number. I want you to focus less on the computation of that number and more so what that number represents. And so if you're already comfortable finding the 2 points, taking the limit as h goes to 0 and finding the number, if you don't need more practice of doing the numerical computations, you can just use your calculator and the dy dx button to get the number for your problem. So let me start with problem 26. So a baseball is projected upward from ground level with an initial velocity of 64 feet per second. Then its height is a function of time given by the formula s of t, and then it kind of flowed between two lines here. It should be negative 16t squared plus 64t. And then I'm asked to calculate the instantaneous rate of change, and in this case, parenthetically, the instantaneous rate of change is going to be how fast the ball is moving at 2 seconds. So let me talk about the graph of this function, what the x and the y-axis mean, and what the units are for the instantaneous rate of change. So if I was to graph this function, on the x-axis I would put the letter t, because the t is kind of where the x position is. And on the y-axis I might write s of t, s probably meaning speed. And I could write y as well, so maybe I'll write y, or s of t. Now I'm going to graph this. Now this is the graph of a baseball. The baseball is going to go up, and it's going to come back down and hit the ground. And I can't imagine it's going to fly for too terribly long. Let me go ahead and sketch a graph using my calculator. And so I'm going to go y equals clear negative 16x squared plus 64x. If I did zoom standard, zoom and went down to option 6, I don't think that's going to be a good window because I think I'm going to miss the top of the flight. So yeah, absolutely. So let me peek at my table and look at the y columns. I see y's like 48, 64, 48, 0, then a bunch of negatives. So that baseball went at least 64 feet high. So the points here, the point 0, 0 says at 0 seconds the ball was at 0 feet. And then at 1 second it's at 48 feet. Then at 2 seconds it's at 48 feet. At 3 seconds it's at 48 feet. And at 4 seconds it's at 0 feet. The next point says at 5 seconds it's at negative 80 feet. So this function, really, its domain in terms of, for this particular problem, would probably be between 0 and 4 seconds. So the ball flies for 4 seconds. And let me adjust my window. And I'm going to change the y max to make it so I can see the top of the ball. The y max is how high the ball is going. And I know it at least went 64 feet. I'm going to make it 100 feet. So that's a better window. So the graph more or less looks like something like this. And let me go ahead and just plot some points here just so you can see them. So from my table, I had a point 0, 0, which meant at 0 feet the ball was on the ground. And then after 1 second, it was at 48 feet. So that would be the point 148. And then at 2 seconds, it's at 64 feet. At 3 seconds, this is 1, 2, 3. 3 seconds, it's back down at 48 feet. And at 4 seconds, it's at 0 feet. It's maybe not the best graph, but it says what I need it to say. So that's a really detailed graph. It turns out that I didn't even need to make any graph at all to do this problem, but I want you to understand the units. So when I'm going to do my instantaneous rate of change, instantaneous rate of change is always going to be in the numerator. It's going to be, I'm going to subtract the y's, so we can say it's the change in the y's. And in the denominator, I'm going to subtract the x's, and it's going to be the change in the x's. And if I'm not looking at numbers and I'm just looking at units, the y is going to be the height, like at 0 feet, 48 feet, 64 feet, 48 feet. So it's going to be the height of the baseball, and that height's in, I'm assuming it's feet because the units here are in feet, so it's going to be the height in feet, and then the time is time in seconds. And when you divide a height in feet by a time in seconds, the units that you're going to get is the feet per second. So when I do my instantaneous rate of change, it's going to tell me at exactly 2 seconds how fast the object is moving in feet per second. So that's why here we wrote velocity, because velocity is distance per time. In this case, it's feet per second. So if I knew something about how a baseball, how the velocity of this baseball changes, I could know the answer to this already. Initially, the ball is moving at 64 feet per second, and then eventually it's slowing down, slowing down, slowing down, slowing down, and it gets to the very top of its arc, and at that moment, it's for that second or that instant, millisecond, it's actually stopped, and then it starts falling down, and as it falls down, it speeds up, speeds up, speeds up, and speeds up. So while it's going up, it's slowing down, and then it pauses, and then as it's going down, it speeds up. Well, at this instant right here, which happens to be the vertex of this parabola, at 2 seconds, it's at the very top of its arc, and it's not moving at all there. So the answer, without even doing any algebra, because I know a little bit of theory, the answer, the instantaneous velocity for this ball, and I'll do the algebra next, is going to be 0 feet per second. That's just knowing a little bit extra, but I didn't have to know that little bit of extra. To find out the instantaneous rate of change, or the instantaneous velocity at t equals 2 seconds, I would need 2 points. The first point would be 2 comma something. The second point would be 2 plus h comma something. And the 2 something, I can just go negative 16 times 2 squared plus 64 times 2, and that I could have also stole from a table. This is going to be the 64. Let me make sure that's right. This is negative 16 times 4 plus 64 times 2, which is negative 64 plus 128, which is 64. So the first point I'm going to use for the instantaneous velocity is the point 264. And then for the next one, I'm going to go negative 16 for this y times 2 plus h squared plus 64 times 2 plus h. I'm going to do this foiling first. That foiling is 2 plus h times 2 plus h. And that foiling, first are 2 times 2, which is 4. Outers are 2 times h, which is 2h. Inners are 2 times h, which is 2h. Lasts are h times h, which is h squared. I'm going to combine the 2h's to a 4h. And now I'm going to clear the parentheses. I'll go negative 16 times 4 is negative 64. Negative 16 times 4h is negative 64h. Negative 16 times h squared is negative 16h squared. 64 times 2 is plus 128. 64 times h is plus 64h. All right. Well, nice things happen. The 64h's cancel. Negative 16h squared is going to hang out first. and a minus 64 and a plus 128 gives me a plus 64. So the y coordinate here is negative 16h squared plus 64. So now I want to find the instantaneous rate of changing. If I wrote that too ugly, it's negative 16h squared plus 64 for the y and 2 plus h for the x. So the instantaneous rate of change, in this case it's velocity in feet per second, instantaneous rate, it's going to be y2, which is negative 16t squared plus 64, minus y1, which is minus 64, over x2, which is 2 plus h, minus x1, which is 2. And I need to sneak in here, so let me write this better. I forgot to write the limit as h goes to 0 of negative 16t squared plus 64 minus 64 over 2 plus h minus h. I can't even copy. That's negative 16h squared. 11 minutes into the video. Sometimes when I screw up like this, I just start the whole video over. But I've already started it over. I don't want to do it again. So let me redo this on a whole new sheet of paper. So my instantaneous rate of change is the limit, sorry about this, as h goes to 0 of y2, negative 16h squared plus 64 minus y1 over x2 minus x1. And that's going to equal the limit as h goes to 0. In the numerator, I'm just left with a negative 16h squared because the 64's cancel. In the denominator, I'm just left with an h because the 2's cancel. Now I can cancel out an h and the fraction goes away. I'm left with the limit as h goes to 0 of negative 16h. Because the h's cancel from the denominator, I'm left with 1 in the numerator. Now I plug in 0 for h. I get negative 16 times 0, which is 0, which is perfect because that is the velocity when you're at the top of an arc in a parabola, or the instantaneous rate of change when you're at the top of an arc in a parabola. So the important thing in this problem is to realize that that instantaneous rate of change needs units in a word problem, and the units are feet per second, because on the graph, the y-axis is the time in seconds, the x-axis is the time in seconds, and the y-axis is the height in feet. I probably could have written feet up there and it would have been stellar. If you want to, for the word problems, if you don't need practice in finding the 2 points and doing the limit to find the numerical instantaneous rate of change, if you want to use your calculator and the dy dx, that's fine. So on this problem, if I wanted to avoid all the grunge, I could have went second calc, went down to option 6 dy dx, typed in the number 2, and it's going to give me the instantaneous rate of change is 0. So for the word problems in this section, if you've had enough practice doing y2 minus y1 over x2 minus x1 with the limit as h goes to 0, then just use your dy dx feature on your calculator to get the numerical answer and focus on the words and what they mean. So pause the video and give problem 25 a crack, and then I'll move into the next problems. So 27 and 28 are more or less just like 25 and 26. In each of our problems, 27 and 28, an object is dropped, and eventually it's got to hit the ground, and the whole time it's going down, it's speeding up. So in problem 28, I have a cannonball dropped from a building, so I have some building. Here's my building. My building is going to be on the y-axis, and it has a height of, I don't know what the height is, but suppose the height in meters, so its height is going to be in meters, and it's dropping for a certain number of seconds. So the function that's given in this, it's this function, f of t equals negative 4.4t squared plus 50, it's going to tell me the height of the ball, or the cannonball, during the time that it flies. So it starts at 0 seconds at some height, and it's going to go down, and eventually it's going to hit the ground. What I want to know is what its instantaneous velocity is at 1 second. So at 1 second, how fast is it moving? And the speed that it's moving is the slope of the curve at, well, I'm saying words that are for the next section. Its instantaneous rate of change is the slope of the line that connects 2 points on the graph that are infinitely close that go through the point 1 comma whatever it is. So what I'm trying to find is the slope of this line. So let me find out what that point is real quickly. So I'm going to graph negative my function y equals clear negative 4.4 x squared plus 50. I think my window is going to be fine. And really the only part of the graph that fits for this problem is the part in the first quadrant. It didn't go up then down, so the part that's to the left of the y-axis really doesn't apply, and it doesn't go beneath the ground unless it's somehow some bonker busting cannonball. So just this little segment of the graph makes sense here. So and let me look at my table. At 1 second, it's at 45.6 feet high. So this cannonball, at 0 seconds, it was at 50 feet. At 1 second, it's at 45.6 feet. At 2 seconds, it's 32.4 feet. The question is, what is its instantaneous rate of change at 1 second? And its instantaneous rate of change at 1 second is the slope of that line that goes through the point 1 comma 45.6. So that's not the instantaneous rate of change. At 1 second, it's 45.6 feet high. The instantaneous rate of change is how fast it's moving. So let me find the instantaneous rate of change, and I'm going to cheat in some sense because I'm well versed enough in doing the points. I'm just going to use my calculator to get that. I'm going to go second calc, option 6, dy dx, type in 1 for 1 second, and it says at 1 second it's moving at negative 8.8. Instantaneous rate of change for objects that are going up and down, the instantaneous rate of change is a positive number when something is getting higher and negative when an object is going lower, because during this portion of the cannonball's flight it's going down. That's why this came out to be a negative number. So my answer for this problem, my instantaneous rate of change is negative 8.8, and I need units. The y-axis is meters, that's height in meters. The x-axis is in height in seconds, so it's going to be negative 8.8 meters per second. So that's all you would have to do for problem 27. If I wanted to, I could have created 2 points. The x-coordinate of the first point would be 1. The y-coordinate of the first point would be 45.6. The x-coordinate of the second point would have been 1 plus h. The y-coordinate of the second point, I would have had to plug 1 point plus h into that function, and then I'd have had to do the limit as h goes to 0 of y2 minus y1 over x2 minus x1. Again, if you feel comfortable enough doing that computation, since you've done enough of those computations that you don't feel like doing more, just use the dy dx feature on your calculator to get the numerical answer for the instantaneous rate of change. But make sure to get the right units on it, because the units are the key here. All right, so give 27 a crack. It should go just like problem 28, and you might be able to do it real quickly. You don't even need to draw a graph for your homework. In fact, you can just, as long as you know what the units of the y-axis and the x-axis are, you know the units for your answer, and you can get the number from your calculator. That's your problem 29. I'll put it back up in a second, or probably be more than a second, after I do problem 30. So problem 30, We have a company selling cell phones, and it says the profit from the sale of X cell phones is given by the formula, and it gives me a formula. So how this formula works, if I plug a number in for X, that represents the number of cell phones that I sell, and the number I get out is going to be the profit. So if I was graphing this function, if I wanted to understand the units, the x-axis is going to be what X stands for. It's the number of cell phones sold. And what I get out is the profit for selling that many cell phones. So the y-axis is going to be my profit. When I'm asked to find the instantaneous rate of change, the units are going to be profit divided by the number of cell phones sold. It's kind of profit per cell phone sold. But before I get on to the instantaneous rate of change, this has a part A and a part B. And the part A is just to help us get used to understanding a new kind of function. So find the profit from selling 1,000 cell phones. There aren't any words in problem 30 that talk about instantaneous rate of change. So this is not an instantaneous rate of change problem. This is simply just understanding how the function works. This wants me to just take this 1,000 and plug it in for the X. When I do P and then put 1,000 in the parentheses, I read this as the profit from selling 1,000 cell phones equals 450 times 1,000 minus 0.055 times 1,000 squared minus 300,000. And I have no chance of doing that without my calculator, so I'll pull out my calculator, try to do that computation, second quit, clear out my main screen, and go 450 times in parentheses 1,000 minus 0.055 and then times parentheses 1,000 squared and then minus 300,000. This is going to be $95,000. So the answer to part A, the profit from selling 1,000 cell phones, is $95,000. So I'm just going to write 95,000 with a dollar sign. That's enough explanation. When I see a dollar sign, I understand that that means money. And I know that it means profit because I'm asked to find the profit. Although it might have been nice if I said the profit from selling 1,000 cell phones was $95,000. That's not necessary. All right, so let me do the next part. Find the instantaneous rate of change at the production of 1,000 cell phones. And then parenthetically, I said the instantaneous rate of change for a profit function, it's not called velocity. Velocity is the instantaneous rate of change when the x-axis is time and the y-axis is distance. When the x-axis is like a number of something sold and the y-axis is the amount of profit, the instantaneous rate of change function is called the marginal profit function. So when I go to write my answer, I could say either the instantaneous rate of change equals, or I can say the marginal profit equals. In business, when you find the instantaneous rate of change of a profit function, it's called the marginal profit function. And for both of these are going to be the same numerical answer, and it's going to be profit per cell phone sold. So my units are going to be, the y-axis is profit, so that goes first, and the x-axis is number of cell phones sold, so cell phone sold. And what the instantaneous rate of change function does, or what the marginal profit function does, is it estimates the profit from selling the next cell phone. So this instantaneous rate of change at 1,000 cell phones, it's going to give me how much money we're going to make for selling the 1,001st cell phone. So this will estimate. So what I'm doing is I'm estimating the profit that will be made when the 1,001st cell phone is sold. All right, with all that done, that's all the theory part of this, and I'm just going to blindly trust my calculator. I'm going to graph this function, and I'm going to get the instantaneous rate of change by just doing dy dx at 1,000, because that's the x value. In order to be able to do that, when I graph this function, I need to get a window that's going to be suitable, and for x min, that's the least amount of cell phones that I might sell, so I'm going to put 0 for x min. It kind of doesn't matter exactly what you use for x min, but for x max, it does matter. It has to be at least 1,000. I'm going to bump it up to 2,000. Just as long as I pick a number that's bigger than 1,000, I'll be able to calculate the instantaneous rate of change when you're selling 1,000 cell phones using my calculator. Now if I want to see the graph, well, the y's are the profit. I'd like to think we're not going to, well, maybe if we don't sell any cell phones, we're going to lose money because you've got costs that you're paying for and you're not getting any revenue to match up with them. But I'm going to make it at 0. It probably should be a negative number, but it's not going to matter for my calculator purposes. And then for Y max, when I sold 1,000 cell phones, I'd make $95,000. I'd like to catch as much of the graph as I can. So I'm going to make my Y max bigger than $95,000. I'm going to make it $200,000. And I don't know that I don't know that I'm going to see the best graph in the world by when I graph it, but I know I will be able to answer this question. As long as my x min or my x range has 1,000 in it, then my calculator will be able to calculate the instantaneous rate of change, even if I can't see the graph as well as I'd like to. So break out my calculator. I'm going to enter that function. So on y equals clear, now 450x minus 0.055x squared minus 300,000. And then set a decent window up. So window x min 0, x max 2,000. And really, the only thing that absolutely matters is that my x range covers the number of cell phones that I'm selling. As long as between the x min and the x max, the number 1,000 occurs, your calculator will give you the right answer without. It might not give you the best graph. The graph might not be, you might not see the entire parabola, but nevertheless, your calculator doesn't care whether you can see the entire parabola or not. It will give you the right number. So I'm going to hit my graph button now with that window. And you see, I didn't go high enough in terms of my y's, but it doesn't matter. Well, let me just make my y's higher. Let me make my y's go up to maybe 500,000. Who knows? Getting better, and I'd have to make my x's bigger, but this is getting ridiculous because I don't care to see the whole. I don't need to see the entire profit function graphed to answer this question. To get the instantaneous rate of change, which is the marginal profit, I just go second, trace, go down to option 6, which is that's the instantaneous rate of change feature on the calculator, and I type in the number 1,000, and it says the instantaneous rate of change is 340 and then dollars per cell phone, which means when I sell the 1,001st cell phone, I expect to make $340. So maybe this is some new iPhone or Samsung Galaxy where they have huge profit margins when they can make $300 for every cell phone that they sell. So my answer, the important part of my answer is that the instantaneous rate of change is $340, I should probably say, per cell phone. I probably didn't even need to write profit. I could have said I'm going to be making a profit of $340 per cell phone, and with the dollar sign it implies that it's a profit because this is a profit function. You could not write the words instantaneous rate of change in your answer, or not write the words marginal profit. As long as you said it's $340 profit per cell phone, whether you included the word profit or not, I think that would be implied because it's a profit function. And that's all you need. That's all I needed to do for that problem. Let me bring in your version of this problem. It's essentially the same problem, except this is a company selling car seats as opposed to selling cell phones. But it's the same kind of idea. The function has the same sort of feel. And you want to pause the video and do problem 29. For part A, you're just finding the profit for selling 800 car seats. You're going to plug 800 in for this. So this equation right here, if you plug a number in for X, that stands for the number of car seats that you're selling, the value that you get out is a total profit. When you do the instantaneous rate of change, it's going to be the profit per car seat. It's going to give you the profit that you are expected to make by selling the next car seat. Here, since we're finding the profit for selling 800 car seats and the instantaneous rate of change at a production level of 800 car seats, the marginal profit, or the instantaneous rate of change, is going to give you the estimated profit for selling the 801st car seat. All right, just two problems left, 31 and 32, I think. Yeah, 31 and 32 are two problems left. And 31 and 32 are a lot like 29 and 30, but instead of having profit, they're giving me costs. So I have a cost function for manufacturing X books. Maybe they're textbooks, so I think they're kind of expensive. And just like my profit question, the first question is find the cost of producing 50 books. Well, because X represents the number of books, to find and because this is a cost function, to get the cost of producing 50 books, I'm going to plug 50 in for X. And I get the cost of producing 50 books is going to be 50 squared plus 30 times 50 plus 50. Lots of 50s in there for me to mess up with. So let me make that happen. So second quit, clear, parentheses, 50 squared plus 30 parentheses 50 plus 50. So it's going to cost $4,050 to make 50 books. So the cost is $4,050. Again, if you just wrote $4,050, because this is a cost function, I'd understand that it's a cost that you're getting. So that's part A. That had nothing to do with, I don't need a graph to find that. I can just use the function. Part B, because it's an instantaneous rate of change, I'd either need to create 2 points or use the dy dx feature on my calculator. And I've done enough of the 2 points, finding the limit as h goes to 0, so I'm going to use the dy dx feature on my calculator. So I'm going to graph this function. So into y1, I'm going to put x squared plus 30x plus 50. And what it's going to give me, it's going to give me a graph. The x-axis is going to be the number of books that are produced, and the y-axis is going to be the cost. When I find the instantaneous rate of change, it always gives me y per x. So it's going to be the cost per book. So what the instantaneous rate of change of this function is measuring is the cost per book. I'm going to find the instantaneous rate of change when 50 books are produced. What it's going to estimate is the cost of producing the 51st book. Because costs change. The more you produce, sometimes the cost goes down because you kind of get quantity discounts. But at some point, as you produce more, your costs go up because maybe you reach your capacity and you have to open up a new building or hire new employees or pay overtime. So your costs could go down or up per book, depending on the quantity and your dynamics of your company. But regardless, the instantaneous rate of change for this function is going to give me the cost per book. And when the x-axis is a object and the y-axis is a cost, the instantaneous rate of change is usually called the marginal cost function. So it would probably be nice if in my answer I said the marginal cost. Marginal, we would usually the cost of the next book is, and let me get there. So I need to graph this function, and I need a decent window. Again, it doesn't really matter if I can see the entire graph. I know that my x's have to encapsulate 50. I'm going to start with 0 books and go up to 100 books. And I might not see the entire graph, but that's okay. I'll see enough of the graph. And for my y's, I know my costs can't be less than 0. And because there the cost was $4,000, I'm going to make the cost bigger than $4,000 because I know I at least need to go that high. And the y's are representing the cost, so I'll make it 10,000. Again, if I don't get the best picture, it doesn't matter. I can find the instantaneous rate of change as long as my x's have the x value in it. Whether I can or can't see the y's, it doesn't really matter. So I bust out my calculator, hit my y equals, do a clear x squared plus 30x plus 50, window x min 0, x max 100, y min 0, y max 10,000. Again, it might not be the best window for this, and it's not, but it's good enough. Now I'm going to find the instantaneous rate of change when 50 books are produced. So I go second calc dy dx, type in 50, gives me the instantaneous rate of change is $130. So the cost of producing the 51st book is going to be $131. So it has to be a pretty expensive book, maybe a textbook that they're paying the author a huge royalty on. So the answer to this question, the instantaneous rate of change at 50 books is $130 cost per book, or $130 per book without the word cost. You don't need the word cost, but because it's a cost function, it's not such a bad idea to have it there. All right, so that's everything for problem 32. And now you need to make a crack at problem 31. And it's just exactly the same. I never try to leave you hanging on word problems, so I will always, if I ask you to do a word problem that has exactly the same skill set in it, and you just need to kind of mimic and try to understand. All right, so pause the video, do that, check your answers. Now we're done with this section. We just have one section left in chapter 1.